All right, so now let's go to the final case. Okay, let's consider the case when we have redundancy. Okay, so in this case, we're going to have more than 6 joints. Okay, so we're going to say n is greater than 6. All right, so what happens here? What happens here? Well, if we consider the 3R planar open chain, okay, ignoring orientation, just considering the position. Okay, by now we all know that there are an infinite number of solutions. Okay, so given Cartesian position of the tip, x, y, there are an infinite number of solutions for theta 1, theta 2, and theta 3, which satisfy this equation. All right? All right, so the problem is, okay, there's no unique solution. Okay, so in this case, what we want to do is we want to formulate the problem in this way. So let's suppose that there's some desired trajectory that the end effector has to follow. Okay, some desired trajectory. And we want to find solutions for theta 1, theta 2, and theta 3 such that it follows this desired trajectory in some desirable way. Okay. All right. So we have x equals f of theta. Okay. So the question is, find theta of t. Okay, that tracks desired x of t. Okay, in some nice way. Okay, in some nice way. Okay. For example, if I'm drawing this line, I don't want my arm to be moving all over the place, right? While I'm doing this. You want the arm trajectory, the joints to be moving in sort of a minimal way, right? In some smooth, minimal way. Okay. All right, so there are many solutions. Okay, so we want to find the best one. Okay, so I told you that last lecture I told you that we'd go back to the results for the optimization problem, right? Okay, so here's how I'm going to formulate it. Okay, so in the general case, we have t. Okay, so let's write the Jacobian equation. So v equals j of theta dot. Okay, so it can be the space Jacobian, it can be the body Jacobian, doesn't matter here. Okay, so v is given. Okay, so that's the desired end effector trajectory's velocity. Okay, so that's my v. J, okay, this is going to be 6 by n. Okay, remember n is bigger than 6. Okay, we're assuming. Okay, and theta dot is n-dimensional. Okay, now, so given v of t, we want to find theta dot of t. Okay, not theta, but theta dot. All right. Now there are what? An infinite number of solutions to this problem, right? Because this is n equations, 6 unknowns. Okay, so theta dot is, sorry, let me, 6 equations, n unknowns. Okay, n is bigger than 6. So here are my unknowns. Here are my 6 equations. So 6 equations, n unknowns. All right, more unknowns than equations. So we have an infinite number of solutions. Okay, so one way to solve for theta dot okay, so this is what we want to find, is the following. Let's do this. Minimize let's find the smallest joint velocity. Okay, subject to the constraint that v equals j of theta times theta dot. Okay, so we're going to pose it as a minimization problem. Okay, so remember this is given. J we know. We're trying to find theta dot of t, theta dot, that minimizes this. Okay, all right, so we know how to do this. Or we should. Right? Let me put a half in front of here, just to make things a little bit nicer. Okay, so how do we solve this? Well, let's go back to the first order necessary conditions. Okay, so first order necessary conditions. Okay, so you remember what they were? Well, here's one of them. Okay, this just comes down directly. Okay, remember the second condition? The second condition was, well, let's write this out. We can write this as 1/2 theta dot transpose theta dot. Okay? So the second condition, check your notes, is theta dot transpose. So you take derivatives now. Okay. Make sure I get this. Let's put a minus lambda transpose j of theta is equal to 0. Okay, now where did this come from? Okay, so recall. Okay, if we had this problem, minimize f of x with respect to x, subject to the constraint g of x equals 0. Okay, so this is a general form. Remember we said that the first order necessary conditions are, right, df dx, right, plus lambda transpose dg dx equals 0. Okay, so replace, so here x is theta dot, f of x is this, 1/2 theta dot transpose theta dot, and g of x is v minus j theta dot, for example. Okay, so apply that to here. This is what we get. Okay, so now we have these two equations. Let's solve for theta dot and lambda. Okay, so from this equation we know that theta dot is equal to j transpose lambda. Okay, so from equation 2. Okay, so let's go over here. Okay, now let me do this now. So let me now multiply both sides of the equation by j. So j theta dot is equal to J times J transpose times lambda. Okay. Now J theta dot, this equals V, okay, from equation 1. Okay, so V is equal to JJ transpose lambda. Okay, so let's write that. So V equals JJ transpose lambda. Okay, now, here's a big if. If J is full rank, then JJ transpose is a square matrix that's invertible. Okay, so in that case, we can write JJ transpose inverse times V is equal to lambda. Okay, so assuming this inverse exists. So when does the inverse not exist? When it's at a singularity. Okay, so we have this. So now let's plug this back into equation 1, or equation 2. Okay, so therefore, theta dot is equal to J transpose, JJ transpose inverse V, okay, from equation 2. So here's one way to solve the inverse kinematics in this optimal way. Okay, so if I have this tracing task, I want this end effector to draw this nice, follow this contour, follow this path in space. Okay, and I have many redundant joints. Here's one way to find it. Okay. Now, if your robot accepts velocities as inputs, you can just put this directly in. If your robot only accepts joint positions as inputs, then you can use standard, right? Delta t minus theta t over delta t is equal to this, okay? Right. So you can do it this way. Right? Okay. So is this a good way to solve the inverse kinematics? Well, it's not bad. It's not bad. You'll have a chance to look at some problems in the exercises, and you'll see that sometimes there are problems. Well, first of all, when this becomes singular, we're in trouble. Okay, it doesn't exist. Okay, so we have to deal with that. And secondly, when you do this kind of approximation, what happens? Like errors build up, right? So eventually, you want to track this trajectory. Initially, it starts doing okay, but as errors build up, you start kind of deviating, right? And so errors, there are ways to deal with that. Okay, here's another one. Suppose this robot's job is to wash windows. Okay, so it's going to do this all day, 10,000 times. Okay, and let's say, well, if it's doing this 10,000 times, this seems like a good way to do it, right? Because you're sort of minimizing joint velocity, so you're doing it in sort of some efficient way. Well, if you use this method, what can happen is that, okay, so here's the path. Okay, so here it is. It's washing windows, tracing. Does it a few times. Goes around once, comes back, and funny thing happens. Okay, it's in a different, doesn't come back to its original configuration, but it kind of drifts. Do this a few more times. Does that. do this 1,000 more times, you know, you end up singularity. Okay? So there's this problem of drift. Okay? So when you do this once, you want it to come back to the same posture. You don't want it to do that. Okay? So there's that problem. Okay? So these are the kind of issues that you have to, you know, the basic idea is sound, okay? But these are some of the problems that you have to deal with when using this method. Okay? Okay, I think this is a good place to stop, so let's stop here.